Okay, so I wanted to jump back to my formal typed up presentation here. So we already calculated these and we talked about how there was an overlap when I looked at them individually. And then when I did the double, when I looked at the actual two sample process, I got that zero wasn't really there, but I kind of justified it as decimal accuracy. But it does bring up the question, which is more reliable? And when I look at them individually, I see that there's no difference, but when I physically subtract them, I do get a slight difference. Um, how do I know? And this is where hypothesis statements are going to come in and sort of make it a little bit easier to definitively say one way or the other if there is a difference between the two proportions. So when we look at a null, the null statement for a two sample proportion test is that when I subtract the two proportions, I should get zero. So we translate that to either the difference is zero or that P1 is equal to P2. The alternative is that the difference could be greater than zero or that P1 is greater than P2. Again, these are interchangeable statements with each other. Or it could be less than, or it could be not equal to, which would be a two-tailed test. And then whenever we're defining these samples for these hypothesis statement, we want to make sure we define out in context what these P1 and P2s represent. Okay, the new concept that we've not had to encounter, but it only shows up with population proportions. One of our assumptions is that the population proportions are equal in the null, so we assume the variances are equal. In which case, we're going to do a process called pooling the variance, which is this lovely formula here where I add up the sample, the successes from the first sample plus the successes in the second sample and divide by the total sample size. Okay, so our formula for the test statistic, we're going right back to Z star, or Z again, I'm sorry. Z star deals with confidence intervals. We're going right back to Z scores. So we need a statistic and a parameter. So at first it's a little on the intimidating side, but we do want to point out one thing, that in a true two-sample proportion test, the population we're assuming is, or sorry, the null we assume is zero. So we really, that term disappears, and we just have to worry about all those p hat terms. Okay, all right, so let's try to piece all that together. Forest in Oregon has an infestation of spruce moths. In an effort to control the moth, one area has been regularly sprayed from airplanes. In this area, a random sample of 495 spruce trees showed that 81 had been killed by moths. A second nearby area receives no treatment. In this area, a random sample of 518 spruce trees showed that 92 had been killed. These data indicate that the proportion of spruce trees killed by the moth is different in the two areas? Okay, so let's remind ourselves of the process. We're going to do assumptions, set up our hypothesis statement, work out the calculations, and then make a statement of conclusion. So assumptions. Do we have two independent samples, two SRSs? And it actually does say it in the problem that there's SRSs. Can we assume normality? And if we go back to, we've got 81 out of the 495 and 92 out of the 518. When I do the NP and n times 1 minus p, I definitely get numbers that are bigger than 5. So as far as that's concerned, we're good for normality. Population is at least 10n. Well, where'd the 10,000, where'd that come from? Well, remember we want to add the two individual sample sizes up. So let me kind of back up a second. We want to add up the 495 and the 518 and then multiply that by 10. And that gives us a reasonable estimate of what our population is. Okay, so then from here we want to set up our null and alternative. And in this case we're going to go with our null would be P1 equals P2. And since I don't really get a sense of directionality, then I can we'll just do a two-tell test. We'll kind of say that I just don't know if they're equal or not. Alright, then we go back and collect up all of our numbers, going back to the P1 and the P2. So let me go back to our original problem. Let me pull out a calculator just so we can recognize what these numbers are. So our proportion of the first sample is 81 out of 495. Which gives us 0.16 for a p hat. And the second one is 92 out of 518. And I get 0.177. So pretty close, but again, maybe the sample sizes are large enough that it would impact the proportions and allow us to think there actually is a difference. Okay, so kind of keep those two numbers handy. Okay, so then we're going to set up our formulas with, let's see, so I'm going to pull up my calculator again, remind ourselves of where we're getting these things. So the 0.16 was from, this 0.16 was from the first sample, and this 0.18 came from the second sample. And then the question is, where did the 0.17 come from? And if you remember, we're going to pool the variances together. So if I pull the variances, can I go back a slide? A couple of slides. Okay, so pull the variance. We want to add the positives and divide by the total sample. Oops. Okay. Alright, so if I add up the 81 and the 92, and then I want to divide that by the total sample, so the 495 plus the 518, and then close that. That's where I'm getting the 0.17 from for the population. So that's this formula here. That's where I get the 0.17 from, is by pooling the variances together. So 0.17, 1 minus 0.17 is 483, and then I have that lovely denominator there. Okay, so let me get my calculator back out again. Let me show you how we get these other numbers from typing in the buttons. So I want to subtract the two numbers. So the 0.16 minus the 0.177. And I got negative 0.039. I'm going to kind of keep that number handy for just a moment. I want the square root, and I'm doing this piece right here, of the 0.17 times the 0.83. Alright, that gives me that number. And then I want to do this piece right here, the 1 over 495 plus the 1 over 518. So 1 divided by 495 plus 1 divided by 518. And I want to take the square root of that one. Okay, and if you remember that denominator, we're multiplying those two things together. So I want to take the 0.062 that I just got and multiply it with the 0.375 from before. Okay, so that denominator is now 0.0236. So I go back up to the 0.16 minus the 0.18, which is that number right there, the negative 0.013. And I want to divide it by that 0.02 that I just found, and I get negative 0.59 for a z-score. Okay, so how do we get the p-value? Well, we're dealing with a norm CDF. So let's go to distributions. We want norm CDF. And if I have a negative z-score, let's cover that up. If I have a negative z-score, I'm on the bottom end of my bell curve. So I want to go from negative infinity all the way up to negative 0.59. So negative infinity would be the negative 1 e to the 99, in case you didn't have it in there. Up to an upper bound of negative 0.59. And then since it's a z-score, we'll keep the mean and standard deviation at 0 and 1. And then hit enter. And it's going to give us a p-value of 0.277, but this is a two-tailed test. So on a two-tailed test, I want to double this. So I get a p-value of 0.055. Okay, so how does that compare to alpha? Our level of significance is 0.05. So we're saying we're not going to get excited unless it's smaller than 5%, and we got a sample that shows up 55% of the time. Kind of a boring sample. So our conclusion would be, since the p-value is greater than alpha, I failed to reject the null. There is not sufficient evidence to suggest that the proportion of spruce trees killed by the moth is different for these areas.